Hi, and welcome to Lecture 3. In this lecture, we're going to look at a couple of specific systems that use Newton's second law. We're going to do this in a way that's a little bit higher level than what you would have seen in an introductory classical mechanics class, and we're going to use some of the tools that we unpacked in the last lecture. All right, the two things that I want to look at today are air resistance and a charge in a magnetic field. So to do that, let's flip over to OneNote, and let's just start going. So first we're going to deal with air resistance. This is a sort of obvious place to start because it's something that everyone knows is there, and yet we totally ignore in the standard treatment in an introductory class. All right, we're going to deal with two models of air resistance. In the first one, we're going to assume that the force of drag is proportional to the speed of a particle. In the second, we'll assume that the force of drag is proportional to the square of the speed of a particle. And we'll see that these give us somewhat different results. All right, let's go ahead and write down Newton's second law in both of these two cases. So if we assume linear drag, then Newton's second law will be as follows. mr double dot is equal to, and before I continue, I've been usually pretty good so far in this course about including the argument, so I would say r double dot of t in my functions. I'm going to stop doing that, in part because it's just cluttering things up, and in part because I think that many sources don't do that. So leaving them out is a good way to match up with what exists out there in the literature. In any case, okay, so we'll get mr double dot. This will set this system in a place with Earth's gravity, and we'll put gravity in the z direction. So I'll be able to say minus mg times z hat. All right, nothing particularly complicated there. And then we'll need our drag force, which is going to be, as I said, proportional to the speed. Now, it should definitely go in the opposite direction of the speed, or of the velocity vector, I should say, since drag should slow a particle down. So I'm going to write this as minus b, here will be my constant of proportionality, times r dot. Wonderful. For quadratic drag, I am going to write a very similar equation, at least for the first part. But now I'm going to need this to be proportional to the square of the speed. The way that it turns out to be easiest to do this is to say that I have a constant of proportionality that I'll call c in this case, times the absolute value of r dot times r dot. And you'll see that this points in the correct direction since it points opposite the velocity vector. All right, now we're going to focus on linear drag first, but before we do anything, it's often a good idea when you encounter new differential equations to categorize them. So both of these diffie-q's have a few interesting properties. The first one is that they're vector differential equations. They're ODEs, which means that they depend on a single independent variable, right? The time in both cases. They are what's called autonomous, and that means that the independent variable never appears in these equations. That can also sometimes give us some simplification. And secondly, they're second order, but the zeroth order does not appear. Which means that in both of these cases, rather than treating these as second order ODEs for the position, I could treat them as first order ODEs for the velocity. And that's a technique that can get you very far in a setting like this. All right. Now, there's one more thing that only applies to the first equation, so only linear drag, which is that this is a linear ODE. Okay, and linear differential equations are the sort of bread and butter of any differential equations class. Linear diff EQs have a lot more strategies to solve them. A linear diff EQ means that the dependent variable, here R, only ever appears as the function itself and its derivatives, never multiplied together, such that I get a linear combination of the function and all of its derivatives. So here I have m times r double dot, I have r dot, and then I am allowed to have terms like this. Now, actually, while I'm dealing with this term, let me add one thing that these two equations share, which is that they are inhomogeneous, which means that they have terms that do not depend on the dependent variable at all. All right. Now, it turns out that we won't need all of these things in this case, but it can be very useful to start trying to actually identify the diff EQs that you see in the wild, especially if you've taken diff EQ, but it was a while ago. That can really sort of key you into what sort of steps you might need to take to solve the equations. All right, without further ado, let's hop in and start solving the linear drag case. The first thing that I'm going to do is non-dimensionalize this equation. Now, let's figure out what are my constants. To do that, I'm going to want to rewrite this equation so that I divide through by m. So I'll have minus gz hat minus b over m r dot. So my constants here are going to be g, b over m, because that's the only way that this constant ever appears. Then I'll have my initial conditions. So I'll have what I'll call r dot naught, and I'll have r naught. All right. So I have 1, 2, and then as many constants as I have dimensions for this, and as many constants as I have dimensions for this as well. So if we're in 3D, I would have 3 plus 3 plus 2, 8 constants. Now, oftentimes, this is where we start to get a choice, because we know that we only need 2 reference quantities, a length and a time, as we learned in the last lecture. And as it turns out, when we have this choice, the choice is between non-dimensionalizing or finding reference constants that do depend on the initial conditions and reference constants that do not depend on the initial conditions. And I'm not saying that there's a right answer here. In fact, as we'll see, there sometimes can be good reasons to do it either way. But in this case, let's non-dimensionalize without using the initial conditions. All right, so if we go through this, we'll find that m over b has dimensions of time. So that can be our t ref. Then we need our L ref, and that will come out relatively easily out of this statement because g has dimensions of acceleration. So if I take g and multiply by something that has dimensions of time squared, I'll get a length. So I'll say m squared over b squared is my L ref. Now let me define c by r over L ref. And I'll define tau to be t over t ref. These are definitions. All right. Now, r double dot. We've already used this strategy in the past. Let me go through this relatively quickly. So I'll get d squared t squared of r is equal to, so I'm going to need to move t ref over to the other side. So I'll get 1 over m over b quantity squared. Then for r, I'm going to express that as, for r, I'm going to express that as c times L ref. So then I'll have g times m squared over b squared times c double prime. And I'm going to use this double prime to make sure that we know that this is c seen as the second derivative with respect to tau, not with respect to t. So this means d squared c d tau squared. Good. Okay, and then I need to do the other side of the equation. So minus g z hat, nothing to change there, and then minus b over m. Now I need to do dt of r, which is going to be minus gz hat minus b over m. Okay, I'm going to get a 1 over t ref here, so 1 over mb. Then I will have an L ref in the numerator, so gm squared over b squared times c prime. All right, let's do a bunch of cancellation, and then we'll go on to the next line. We see that here the m squared over b squared cancels with this m squared over b squared. And then over here in the last part of this equality, I have what? So in this case, I have a b squared, b over m. This is also a b over m. And that cancels with my m squared over b squared. So these two cancel with this one. Then the g's on the two sides also all cancel. So when all is said and done, I have c double prime is equal to minus z hat minus c prime. And that's all there is. Okay, so now we're in a good place to actually start solving this equation. And I'm going to point out that there are basically two ways that you could approach it. Method one, which I'm not going to follow, but you should go ahead and check out, is that I could treat this as a first order ODE in C prime. And then once you solve that, you'll get a new differential equation for C prime. And then you can solve that for C. And this works absolutely as anticipated. So go ahead and try it out on your own. Method two, I can treat this as a second order. Inhomogeneous, linear ODE. And I'm going to do this way just so that we get some practice solving this kind of differential equation, which you will have seen before if you've had a class on differential equations, but it always pays to practice. All right, so our job is that we should always put all of the things that depend on this dependent variable on one side. So I'm going to rewrite this equation as c double prime plus c prime is equal to minus z hat. An immediate thing that you might be concerned about is the fact that, I seem to have a vector equation. And fair enough, we do have a vector equation that makes things a little bit more challenging. But it turns out that the same techniques apply as if we did not have a vector equation. So we're just going to proceed as usual. All right. Our strategy for solving an inhomogeneous equation like this is to split it into, split any solution C into two parts. C is equal to C H, which is called the homogeneous part, plus Cp, which is called the particular part. So Cp is any solution to the diffie-q. Ch solves a related diffie-q, namely the diffie-q without the inhomogeneous part. So Ch double prime plus C prime H is equal to 0. All right, so now let's split these into two tasks that we need to do, and we'll do one first. Okay, so we need to just guess any solution to this differential equation. And a good way of trying to solve differential equations like this is to assume that the highest order derivative is 0. So if this happened to be 0, then I would just need to find any vector valued function such that C prime is equal to minus z hat and C double prime is equal to 0. So it looks like a linear function would work here. So what if I say C P is equal to minus t z hat, and I just try that out. Then that would give me that C prime P is equal to minus z hat, and not t, of course, tau. Sorry about that. So this gives me that C prime of P is equal to z hat, and C double prime of P is equal to 0. So this works. I do, in fact, get that C P double prime plus C P prime is equal to minus z hat. Great. So I have my particular solution. Now I need to find my homogeneous solution. So I want to solve CH double prime plus CH prime is equal to 0. The way that I typically do this is using the so-called characteristic polynomial. That means I'm going to create a polynomial in a new variable. I'll use the variable q. And as the coefficients of the polynomial, I'm going to take the coefficients of these terms here. So this is going to work anytime you have constant coefficients on your ODE here. So both coefficients are 1. So this gives me the characteristic polynomial. Let me just write it out. Polynomial q squared plus q is equal to 0. Now the way that I proceed is by finding the roots of the characteristic polynomial. To do that, in this case, I can just factor it. So this would mean that, this is the characteristic polynomial, q squared plus q. Now I want to find the roots, and that's going to help me. So I have q times q plus 1 is equal to 0 to find the roots. And this implies that the roots are q equals 0 and q equals minus 1. Okay, this is good because our roots are distinct, which means we get to do what is typically simpler, which is to say that CH is equal to one coefficient. Let me just call it A. And A is going to be, in this case, vector valued because I have a vector valued ODE here, times e to the minus, so the first root times tau, so 0 times tau, and not minus, sorry, just to the first root times tau, plus b, which again is going to be vector valued, times e to the second root, so minus 1 times tau. Now 0 times tau, that's just going to give me 1, so this is just a plus b e to the minus tau. Good. Now, it would be often the strategy, if this had been the differential equation that we had been given, to now use the initial conditions to solve it. But that's not going to be the strategy here. First, we're going to stick the homogeneous and the particular solution together. Then we will insert our initial values. Okay, so all of this implies that C is equal to A plus B e to the minus tau minus tau times z hat. Good. All right, now we're ready to start sticking in our initial values. So let's go ahead and do that. In this case, it's going to make sense to start with C prime, which I've written up here. It's pretty straightforward to get it from C now that we have the full solution. So what do we have? For C prime at tau equals 0, we'll say that that value is C prime 0. That would be something we were given at the start of the problem. Okay, and we know that it's equal to minus B minus z hat. This allows us to solve for B. I just need to move B over to this side of the equation and C naught prime over to that side of the equation. So I'll get that B is equal to minus C naught prime minus z hat. Good. Now I can solve for A by noting that the initial condition, or the initial value, for C at tau equals 0 will be some given. I'll call that C naught. And that's going to be A plus B, since the e to the minus tau will be 1. And then minus 0 times z hat. But that means that I don't need to add anything. Wonderful. Now we'll stick in what we know B to be. So that's minus C naught prime minus z hat. Good. And this allows us to solve for A. A is going to be equal to C naught plus C naught prime plus z hat. All right, that means that we're ready to write our final solution, which is that C is equal to C naught plus C naught prime plus z hat plus, maybe it's better to just combine this into an overall minus sign, minus C naught prime plus z hat e to the minus tau minus tau z hat. And now that I've done this, it actually seems to make sense to start combining things based on their coefficients. So let me take all the stuff that depends on C naught prime, and I'll group that, and all the stuff that depends on z hat, and I'll group that as well. And if I do that, I'll get that C is equal to C naught plus, okay, so I'm going to need 1, and then minus e to the minus tau, C naught prime. Good. And then plus 1 minus e to the minus tau minus tau z hat. Great. Okay, so I'm at the final form of the solution, and what's left is to try to gain some intuition about what's going on with it. So maybe the most obvious way to do that is, because we're in non-dimensional, in a non-dimensionalized version of the solution, we're already ready for plotting. And that's actually one of the great things about non-dimensionalizing. Plotting something often requires choosing what scale to set, but we've already figured out the correct scale for the problem. All right, so I'm going to hop into Mathematica, which is a great software for plotting, and I'm going to plot the solution. Now, I still have C naught prime and C naught as unknown variables, so I'm going to have to use a manipulate function to allow me to change those on the fly. But notice that I really don't need to worry about C naught itself. That's just going to move the solution vertically up and down. The other thing is that I would have to plot every direction independently, but it looks like the most interesting things are going on in the z direction. So I'm going to plot that first. All right, so I'm going to ignore C naught, since as I said, that just moves things up and down. I'll have 1 minus e to the minus tau times C naught prime plus 1 minus e to the minus tau minus tau, minus tau. And this is in the z hat direction, or in the z direction, so no z hat needed. And I want to plot this from, let's say, tau goes from 0 to 3. Chose that relatively arbitrarily, but we can look at the solution and iterate if we need to. And now I want to manipulate this for different values of C naught prime. Maybe I'll let it go from -2 to 2. All right, so what does my solution look like? Well, if I have C naught prime start out as negative, then my object goes down. That's good. If I have my solution start out, or my velocity start out as positive, then it goes up. That's also good. But does this look like what we would expect if there were no drag? That's not actually obvious. And that's because we have chosen a non-dimensionalization that doesn't allow us to easily compare to the case of zero drag. Remember that the case of zero drag would be the case that b is equal to 0. But we put b in the denominator of t ref. Remember that t ref is m over b. And so we actually cannot do that comparison right now. But at least we can look at some sort of standard features of the solution. It is the case that if we shoot the particle up, or the ball or object up, it comes down eventually. That's something that we would anticipate. And then another thing that's interesting, actually, if I let this go just a bit further, so let me say I let it go out to 10, is that over time, this becomes a straight line. And that it doesn't actually matter how I start the velocity. That straight line is called the terminal velocity of the problem. And now that we've seen it in the solution, let's look for it up here in the functional form. So what happens if I take the limit as t, or as tau, sorry, goes to infinity? So limit as tau goes to infinity. And I don't want to look at the limit as tau goes to infinity of this thing. Instead, I want to look actually at c prime. So this, let's recall what the form is of that. So it was minus b to the e to the minus tau minus z hat. So this is going to be the limit as tau goes to infinity of minus b, so c naught prime plus z hat, e to the minus tau minus z hat. Okay, but as tau goes to infinity, e to the minus tau goes to 0. So this is just going to be equal to minus z hat. So there we have it. As our object continues to go on forever, it hits eventually some terminal speed. And this is consistently what we see in drag problems, a terminal speed being achieved by an object as it falls through the air. All right, and this came right out of our solution. All right, now it's a good time to redimensionalize the problem because we've encountered an object of interest, terminal speed. But because we're in non-dimensionalized, because we're dealing with non-dimensionalized quantities, all we need to do to figure out the redimensionalized version is multiply by the combination of reference constants that has the correct dimensions. So the terminal speed is -1 because it's just the coefficient of this minus z hat in non-dimensionalized quantities. And recall that T ref is equal to m over b. L ref is equal to g m squared over b squared. That means if I need to make a v ref speed, that's just going to be L ref over T ref. So that's going to be G M over B. Okay, so that means that my terminal speed is just, well, minus that. But I guess if I want a speed, I should probably take the absolute value, right? So I'll just say it's 1 in non-dimensionalized quantities. So look, I have terminal speed is exactly equal to mg over b. And again, this gets at this idea that reference quantities are often what you would guess the answer to be once you've found them. Now, I want to comment a little bit on this solution before we move on to quadratic drag. And it's just to say this. Recall that I mentioned before, we aren't able to compare to the non-drag or the no-drag solution with this choice of non-dimensionalization because we defined Tref using B, I should say Tref and Lref using B in the denominator. And so we can't send B to 0. However, if we non-dimensionalized instead of using B, but instead using the initial velocity as one of the parameters, then we could compare to the case where there's no drag. And that would give us another set of interesting answers. So which non-dimensionalization that we use is not sort of set in stone. There's no unique right answer. Different choices can give us different answers to different questions. And what you choose sort of depends on the kinds of questions that you want to answer. So I encourage you to go through this again and try it all over again, non-dimensionalizing, again, using the initial velocity rather than using B. All right, now let's go ahead and focus on quadratic drag. So just to restate this, the differential equation, I have mg is equal to mr double dot is equal to minus mg z hat minus c times r dot absolute value, or length, let me say, times r dot. Good. Now in this case, the non-dimensionalization is a little trickier. Again, I encourage you, if it ever gets tricky, to try using this dimensional matrix D and solving that way. But if you don't want to, or just because I want to save some time, I'm going to skip right to the solution. So here, my reference length, Lref, is equal to m over c, and my reference time, Tref, is equal to m over gc. As you might anticipate, the non-dimensionalized version of this is going to be c double prime is equal to minus z hat minus length of c prime. All right, so where do I go with this case? Well, I could try to treat it, given the fact that it is a first order ODE for C prime. And in this case, because it's not linear, I would really have to write it out in terms of a system of ODEs for the components. So let me quickly go ahead and do that. I would have C double prime in the x direction is equal to, well, in the x direction, there's no z hat. And actually, let me go ahead and assume that I only have x and z in this case. I'm going to ignore the y direction and just put this motion in the xz plane. All right, so in the x direction, I have no z hat component. Then I just have minus, okay, so c prime the length, but that is going to be equal to the square root of cx prime squared plus cz prime squared. All right, and then times the x component of the c prime vector, so that's cx prime. Now in the z direction, I'll have cz double prime is equal to minus 1 minus this same factor here, the length of the xc prime vector, xx prime squared plus xz prime squared, and now times xz prime. And immediately you'll see that this equation is much more complicated. We have a system of two coupled, because they both involve both x and z, non-linear differential equations that are first order in xc prime x and xc prime z. It turns out that these two equations have no analytical solution. But we can look at solutions in specific cases. So I'm going to look at the solution when we only have motion in the vertical direction, so where we have no x motion. In that case, cx prime, so let me say special case, only vertical motion. So that's going to mean that cx is equal to 0 and cx prime, because I'll put it, say it's vertical motion, and I'll just say it's on the line cx equals 0. And I'll have cx prime is going to be equal to 0 as well. All right, so now I only have one relevant equation, which is this one. So I'll have cz double prime is equal to -1 minus, okay, now I need the absolute value of cz prime. Since I'm taking the square root of the square, that's the absolute value, and then times cz prime itself. All right, the presence of the absolute value splits us into two different cases. In one of them, I fire the object, the projectile, up, so that cz prime at time t equals 0 is positive. Then this absolute value spits back cz prime, and this whole term will start out being negative. In the second case, I fire an object downward. Cz prime starts out being negative, so this absolute value ends up negating cz prime. So I have a positive from this absolute value, but then the negative from this. Then that negative combines with this negative sign, so this whole term ends up being positive in the second case. Okay, so I'm going to kick us into an even more special case, the one where we have downward initial velocity. And that's not for any particular reason other than I want to look at some specific forms of the solution. And so we need to specify which case we're in. So in this special case, I'll have cz double prime is equal to -1 plus cz prime squared. And the way that I get that is that this cz prime is going to be minus cz prime at all points in time, actually. Because, or I should say, this absolute value of cz prime is going to be minus cz prime. And that makes sense. If I fire an object downward, even if it has drag on it, it's always going to be moving at least downward. It's never going to switch directions. All right. Now it's time to try to solve this equation. And again, I want to think of cz prime as being a variable. So I'm actually going to switch notations here. I'm going to say that v is equal to cz prime, so that I can restate this differential equation as v prime is equal to -1 plus v squared. All right. Now, how do I solve an equation like this? This is a type of equation called separable. Separable equations are ones where I can get the dependent variable alone by itself on one side of the equation, and the independent variable by itself alone on the other side of the equation. As we mentioned up at the top, this equation is actually autonomous, which means it doesn't depend on the independent variable at all. So it's often easy to figure out ways to make this kind of equation separable. Now, I'm being a little bit tricky here, actually, because in order to do this, I need to think of this object as splitting into dv and d tau. And to make the independent variable all on one side, I need to move the d tau to the other side. All right, so I'm going to do that. I'm going to take this equation and say it's dv d tau is equal to minus 1 plus v squared. Then I'm going to turn that into dv over minus 1 plus v squared is equal to d tau. All right. And actually, as it turns out, it's going to be a little bit easier if I switch the negative sign and put it over here. This is a heuristic for how to solve so-called separable differential equations. But it should always work. All right. So now I'm going to integrate this left-hand side. This is one of these places where you can either remember your trig integrals, or if you're ever in a pinch, you just head into your favorite integrator of choice and you ask it what is the value of an integral like this one, which, as you'll see in this case, resolves into these logarithms, or resolves into the arctangent function. So arctangent of v is what I need. So this implies if I now integrate both sides, that tangent inverse of v is equal to minus tau. Or, and I should say, sorry, plus a constant. Or if I take the hyperbolic tangent of both sides, this would tell me that v is equal to tangent of tau plus, let me name this constant, I guess I'll call it c. Okay, and before I go any further, I made an error here. Of course, when I take the hyperbolic tangent of both sides, I need to preserve that minus sign there. Okay, now I can go ahead and solve for c using my initial condition. So c, I'm going to use the initial condition that v at tau equals 0 is going to be some fixed value. I said that I fired this object downward with some initial velocity. Now, to encode the fact that I'm doing this downward, I'm going to put a minus sign here, and then I'll call the initial speed v naught. Remember, this is non-dimensional speed, so it's a little weird, but that's okay. Okay, so now I can go ahead and stick that in. This implies that tangent of c is equal to minus v naught. And that allows me to solve for c quite easily. This means that c is equal to minus hyperbolic tangent inverse of v naught. The minus sign is allowed to go right through the hyperbolic tangent inverse function because hyperbolic tangent inverse is an odd function. All right. So, great. Now I need a trig identity to reduce my solution. I'm going to need that the hyperbolic tangent of x plus y is equal to the hyperbolic tangent of x plus the hyperbolic tangent of y over 1 plus the product of those hyperbolic tangents. Great. So in this case, my x is equal to minus tau, and my y is equal to minus hyperbolic tangent inverse of v naught. All right. Now I'm going to use this to reduce everything. So what am I looking at? First, it's going to be a minus hyperbolic tangent of tau. Then it's going to be a minus v naught because I'm looking at hyperbolic tangent of hyperbolic tangent inverse of v naught. Okay. then 1 plus. Now, both of these hyperbolic tangents are going to be negative in this case, so I retain the positive sign, and I'm going to get v naught times hyperbolic tangent of tau. Great. And this is a pretty good form for the solution. Let's make sure that it has the properties that we want. If tau is equal to 0, then these hyperbolic tangents of tau become 0. And I'm just going to get 0 minus v naught over 1 plus 0. So minus v naught, as expected. As tau goes to infinity, on the other hand, I'm going to get, well, recall that hyperbolic tangent of tau is going to go to 1. That's a well-known property of the hyperbolic tangent. And so I'm going to get v is equal, or goes to, I should say, minus 1 minus v naught over 1 plus v naught. But that's just minus 1. So it looks like in this case also we have a terminal speed for the object, which is minus 1 in the non-dimensionalized variable. So if I redimensionalize this, I see my terminal speed is exactly the speed that I would form from my dimensionful quantities for my reference constants. My reference constants here are L ref and T ref, given like this. So I'm going to have V ref times, again, minus 1, but I just want the speed here. So M over C times the inverse of T ref, so G root GC over M. And that is going to be root G over MC. No, root mg over c. All right, so now we have another terminal speed to compare to. And I want to point out why this is so useful. Even without working very hard, we were able to get the terminal speeds in the two problems. That means that we could calibrate our models in both cases. For instance, if we were in a context where we didn't know if a linear drag model or a quadratic drag model was more appropriate, we could say, well, we find the terminal speed of our object in this setting, and we calibrate either B or C to that value. Now we can look at the form of the solution at other times to see which model was more accurate. And that's a hugely useful thing that we were able to do just by looking at these few properties of the solution and some limits. All right, there's quite a lot more that we could say on air resistance. And solving these drag problems in many different contexts, analytically and numerically, is great practice with doing this kind of ODE solutions in classical mechanics. But I think it's a good time to move on to our second topic of this lecture, which is a charge moving in a magnetic field. All right, so a charge moving in a magnetic field. Let's go ahead and write down Newton's second law using the Lorentz force law. So as usual, on the left-hand side, I'm going to have mr double dot. And then I know that the Lorentz force law, if I have a charge with charge q, is going to be qv, so r dot, cross b. And then there's not going to be any electric field in this case. This is going to be all that we are interested in. Now, without loss of generality, let's just put B in the Z direction, since we haven't actually fixed any of the directions of the problem yet. So I'm going to say B is B times Z hat. There are several ways that we could work on solving this differential equation. But first of all, let me go ahead and non-dimensionalize it. So we'll start out by just saying that r double dot is equal to q over m times qb, over m times r dot cross z hat. All right. And I'm going to allow b in all of these solutions to be uniform, so that b really is just a constant. Okay, what are our constants in the problem? Well, as we see here, we have this qb over m quantity. And if you go ahead and check, this is an inverse time. In other words, it's a frequency. I'm going to give this the notation omega sub b. And as we'll see, this plays a really important role in magnetic physics. This object is called the cyclotron frequency. Great. But we're going to need more constants than that. We also have our initial, so I'll call that r naught, and r naught dot. So we also have the initial speed. And in this case, because we only have one constant in the equation itself, we're going to need some of the initial conditions to do our non-dimensionalization. Okay. So how to proceed? Let's choose as our time, t ref is just the inverse of this of omega, except if we choose that, we end up, well, okay, either way that we do things, if we choose omega b, or 1 over omega b to be our time scale, we'll end up with some 2 pi's in places. And if we choose 2 pi over omega b, then we end up with some 2 pi's in some other places. So it's sort of arbitrary, but I'm going to choose 2 pi over omega b to be my t ref. And then L ref, well, I'm going to need to use r naught dot. So I'm going to say that in fact, back up. Now I need to figure out L ref. And it turns out that I actually have some good choices and some bad choices to make here. So as I said before, there's no correct non-dimensionalization, but there are going to be some unhelpful ones for sure. It turns out here that the most useful thing to use is going to be not the magnitude of the initial velocity itself, but the magnitude of the initial velocity only in the x directions and the y directions. So I'm going to call that u naught, which is x naught dot squared plus y naught dot squared, square root. And we'll see why I made that choice in a little bit. Okay. So, and sorry, this is, I'll call this v ref because it's a velocity. So then to get L ref, I would just say that's t ref, v ref times t ref. All right. So I'm going to go ahead and non-dimensionalize this equation. It's not particularly interesting as it's exactly the same as the non-dimensionalizations that we've seen in the other problems, but I urge you to try this yourself, certainly. Actually, let me do it. Okay, so let's go ahead and non-dimensionalize this problem. As usual, I'm going to get an L ref. So I could actually think of that as a V ref over T ref outside here times C double prime. That's going to equal QB over M times V ref C prime cross Z hat. Okay, let me actually insert what all of those things are. So I'll get U naught over 2 pi omega b moves to the numerator. C double prime is equal to omega b times vref, which is u naught, cross z hat. Oops, and I forgot my c prime. All right, so now when all is said and done, our differential equation becomes c double prime is equal to 2 pi c prime cross z hat. Good. All right, now there are 3 methods I can think of for solving this ODE. Method 1 would be to write it out as a system of equations. In other words, write out the x coordinate, the y coordinate, or x component, y component, and z component. And that's fine. That will work. It's very ugly. So go ahead and try it if you want, but I'm going to move on to method 2, which is to use complex analysis. Now, this is going to seem like it comes a little bit out of left field because this method won't work in general for solutions to ODEs, but when it works, it's sort of the exactly correct solution for the problem at hand. So let's show it off, and then we'll try another method as well. All right, so the first thing that we're going to need to do, even though I just said that we wouldn't have to do this, is split our problem into the x and y directions and the z direction. So I'm going to write these vectors with 2 components, which is going to look a little weird, where the first 2 components are going to be an xy vector, and the last component is going to be a z vector. This will make sense in a moment. So what do I have? I have x double prime xy, and then c double prime xy, and then c double prime z as my 2 components. This is going to be equal to 2 pi times the vector c prime xy, c z prime, cross, okay, well, what does the z hat vector look like in this setting? It's going to be 0, 0, 1, or sorry, 0 vector times 1. 0 vector with a 1 beneath it. Good. All right. Now, this may not look particularly intuitive here, but the thing I want to note is that on the right-hand side, in the z direction, we're taking the cross product of a vector with the z hat vector. In other words, with a vector pointing in the z direction. That cross product is going to be perpendicular to the z direction. And so it has no component in the z direction. So this looks like some question mark in the xy direction, but then a 0 in the z direction on the right-hand side. This means that in the z direction, our diffie-q is cz double prime is equal to 0. In other words, in the z direction, the particle is just moving at a constant speed. And this makes perfect sense. The reason that it's moving at a constant velocity in the z direction is because there's no force on it in the z direction. Magnetic fields always exert force in a direction perpendicular to the magnetic field. And since the magnetic field here is uniform and in the z direction, it's never exerting a force in the z direction itself. So the particle experiences no force and therefore moves at a constant velocity, Newton's first law. All right, that leaves the first 2 directions. And so I'm actually done using this notation. I'm going to go ahead and now just write our vector c and forget entirely about the z direction. This is now a 2-dimensional vector. Okay, so c double prime is equal to 2 pi times, well, what happens if I take an x hat vector and a y hat vector and I cross them with a z hat vector? Let's actually write it out. So we'll get cx prime x hat plus cy prime y hat cross z hat. And there are some rules for what happens when I take the cross products of x hat, y hat, and z hat. X hat cross y hat is equal to z hat. X hat cross z hat is equal to minus y hat. Y hat cross z hat is equal to x hat. And y hat cross x hat is equal to minus z hat. Z hat cross x hat is equal to y hat. And z hat cross y hat is equal to minus x hat. Sometimes relations like these are called cyclic. And you can see why. If I move x, y, and z sort of all in the same direction while looping around, then I retain a positive sign on the right-hand side. And similarly for a minus sign on the right-hand side. All right, so that means that this is going to give us 2 pi times c x prime. X hat cross z hat is minus y hat. And then plus cy prime, y hat cross z hat is positive x hat. Okay. So I could write this as y prime, cx prime with a minus sign. All right. So now we have our equation written sort of inelegantly like this. And this is where using complex analysis turns out to be a huge help. So what happens if I define a new variable, which I'll call c? It's a little bit of a strange notation, but this is going to be a complex variable. Its real part is going to be cx, and its imaginary part is going to be cy. Now, summing things and multiplying them by constants, all of that is linear, and the derivative goes right through it. So that implies that c prime, if these are functions of tau, is equal to cx prime plus I cy prime. All right. What happens if I take a second derivative? Same thing. C double prime is equal to cx double prime plus I cy double prime. Now, I could go that direction. I can also do another thing based on this second equality here. What happens if I multiply by I? In fact, let's multiply by, let's start by multiplying by I. So I c prime is equal to I cx prime minus cy prime. That's what happens when I multiply I with another copy of I get a minus sign. If I multiply everything by a minus sign at this point, I get minus, minus, and plus here. Great. All right. So now, if I were to write this right-hand side, this left-hand side here, in terms of cx and cy, I would get cx double prime, cy double prime on the left-hand side is equal to 2 pi cy prime minus cx prime. And I hope you can see where I'm going with this. I can actually get away with writing down this system of two equations as the real and imaginary parts of a single complex equation. So I can write c double prime, which remember is this, is equal to minus 2 pi I times c prime. And let's just make sure that this works out. So this is going to give me cx double prime plus I cy double prime is equal to minus 2 pi I cx prime plus I cy prime. But then if I do the same steps on the right-hand side that I did above, I'll get minus 2 pi times I c, actually, I'll include the minus sign inside here. 2 pi times minus I cx prime plus cy prime. And because part of this is real and part of this is imaginary, I can equate the real parts and the imaginary parts. So the real parts are cx double prime and 2 pi times cy double prime. But that's exactly the equation that I had up here. And I can also equate the imaginary parts. So cy double prime and minus cx prime. And that's exactly what I had here as well, including the minus sign. And that's why this strategy works for this problem specifically. If we didn't have this minus sign here, things wouldn't work out in the same way. All right, so I got away with writing my equation like this. Now the question would be, can I just solve it as if it's an equation for a single variable problem? And the answer is yes, I absolutely can. So how do I solve a problem like this? Well, there are lots of ways, but it's a second order linear differential equation. And in fact, maybe it's even easier to just solve it as a first order ODE in Xi prime. So yeah, I think that's the way I want to do it. Yes, let's solve it as a first order linear diff EQ in Xi prime. So I'm going to express this as Xi double prime over Xi prime is equal to minus 2 pi I. But the left-hand side I know is the log, is the derivative dd tau of the log of Xi prime. Now I can integrate both sides and then exponentiate. This is going to give me Xi prime is equal to some constant, I'll call it C, e to the 2 pi I, minus 2 pi I times tau. Okay. And then I can integrate again. So now that means that C is equal to another constant, let's say B. Back up. Okay, now I'm going to input my initial condition. So in this setting, my initial condition is going to be an initial condition for Xi prime, which is going to be whatever my Xi naught x was. So maybe I'll call it Xi x naught prime plus I times whatever my initial condition was for y. All right. So I'm going to get Xi naught prime is equal to C. All right. Nothing particularly interesting there. And now I can integrate both sides of the equation to find Xi. So Xi is equal to Xi naught prime. So I should say so I guess I'll just pull this down. Minus 2 pi I in the denominator. E to the minus 2 pi I tau plus a constant, a new constant, which I guess I'll call K. All right. I can move this minus I to the numerator and turn it into an I. So I get I Xi naught prime over 2 pi e to the minus 2 pi I tau plus K. And what is k? Well, I'll need to set this equal to 0 and then move things around to solve for k. So I'll get c naught is equal to I c naught prime over 2 pi plus k. That implies that k is equal to c naught minus I c naught prime over 2 pi. All right, so when all is said and done, c is equal to e to the minus 2 pi I tau minus 1 times I c naught prime over 2 pi plus c naught. All right, and with that, we are done with this solution in using complex analysis or complex variables. The only thing that would be left to do is if we wanted to find Cx, that would be equal to the real part of C. And similarly, Cy would be equal to the imaginary part of C. But before we sort of jump the gun on that, let's just look at this complex solution. It's going to give us an output in the complex plane, but the complex plane looks like 2 dimensions. And so in some sense, it already gives us the graphical tools that we need to figure out what the solution looks like. Now, anytime you see e to the something times your independent variable, that is going to trace out a circle in the complex plane. The only difference here is that that circle is going to be shifted by some amount in the complex plane. And that amount is going to depend on these constants. So in other words, that circle is both, and I should also say, sorry, it doesn't necessarily start right on the x-axis or right at the horizontal. So it's a circle starting at some point in along the path of the circle, and where that circle is not necessarily centered at the origin. But in any case, this gives us what we expect from sort of a physics 1 or 2 class, uniform circular motion. Great. Now I'm going to let students figure out the details, any more details of that method on their own, because I want to look at a third method here that is, I think, a little bit more advanced than is often taught at this level, but I think is worth including. I think it does something to modernize the way that we're doing things. It feels a lot more like what's often done in modern algebraic sort of style mathematics. Okay, now in method 3, we're going to start again with our equation here. Good. And what I'm going to use here is the fact that of a cross product of A on B, so A cross B, looks like a linear operation of A acting on B. And what I mean by linear is if I stuck in A cross, for instance, B plus C, that would distribute nicely. If I multiply A by another constant, then that works linearly as well. It's a linear function if I think of it as a function on B. And any linear operation can be thought of as a matrix. And so that is the key. I can think of A cross B as a matrix. So in particular, A cross B, these are 3-dimensional vectors because we're dealing with cross products, is going to be equal to the matrix 0, 0, 0 down the diagonal times, okay, so up here, I'm going to get minus, so this is, the way to remember this is the 1, 2 entry. So I'm going to get A3 here. Then I'm going to get minus A2 here and A1 here. And then on the other side of the diagonal, I'll just get the negative. So this is an anti-symmetric matrix. Minus A3, positive A2, minus A1 here. And then that times B. Good. All right, let's just really quickly do one double check that this works. So I know that x cross y is equal to z hat. X hat, I should say, cross y hat is equal to z hat. So let's check that that works. So x hat is going to have a 1 for a1 and then a 0 for the other two. So I'm going to get 0, 0, 0, 0, 0, 1, 0, minus 1, 0. And then y hat is 0, 1, 0. And what's that going to be equal to? Well, in the first column, sorry, in the first row, I'm going to get 0 since I have a 0 in this first row. In the second row, I'm going to go across this row and down the one column, and I'll get 0 again. In the third row, I will get a minus 1. So I think I flipped all of my signs here. So this should have been a plus a3 minus a3 plus a2 minus a1 plus a1 minus a2. All right, so if I do that flip correctly, then I, as expected, get back to 0, 0, 1. And just to check that this works, if I stick in z hat here, then I will put a 1 down here. And now I still get a 0 for this first row. I get a minus 1 for this second row. And I get a 0 for the third row. So that is, in fact, minus y hat. Okay, all is well and good, and we can proceed. So I can rewrite this equation now. And the way that I can do it is by remembering that the cross product is anti-commutative. So if I flip the order of the products, I need to add a minus sign. So this is also minus 2 pi z hat cross c prime. All right, no problem. So c double prime is then equal to, okay, well, I'm going to write a matrix. So I'll put up my minus 2 pi out front. And then I need the z hat vector. But that is going to give me 0, minus 1, 0, 1, 0, 0, 0, 0, 0 as a matrix. All right, and then times c prime. Great. The clever thing that I'm going to try to do here is just call this matrix anything. I'm going to call it M. Actually, sorry. Before I do that, let's do one more step. Just as before, what this is actually telling us, if we look at it carefully, is that the z, that c double prime z is equal to 0. So let's see where we would get that. C double prime z is going to come from the bottom is going to come from the last row of both sides. I get the last row of the right-hand side by cross multiplying this row of zeros with my column vector. But a row of zeros times a column vector is always going to be 0. So this comes from the third row of both sides. But I know how to solve that equation, so I don't need to know what's going on in the z direction. Instead, let's worry about what's going on in the x and y directions. Okay, so now I'm going to reduce my vectors to being just two-dimensional vectors. So I'm going to get the following: minus 2 pi times 0 minus 1, 1, 0 times c prime. Okay, and I'm totally allowed to do that. No problem, since I already know what's going on in the other direction. And the z direction doesn't affect the x and y directions in this case. All right. And a nice thing about this matrix is that while this matrix up here was not invertible, this one down here is invertible. And I'll see that that's important in a second. Because I'm just going to call this whole object the matrix M. So I'm going to say that this is just M times C, and I'll double underline matrices, M times C prime. All right. Now, you might wonder, this looks just like a first order diffie-q with constant coefficients. What if I could treat it like a first order diffie-q with constant coefficients? Can I do that? And the answer is, amazingly, yes, you can. Now I know how to solve, let's recall what would happen. So what would happen if I had the equation f prime is equal to some constant times f? Well, I would look for solutions of the form f is equal to e to the c times t times some constant, let's say f naught. And the reason that that works is because f naught is a constant, and then when I take the derivative, I'm going to hit this e to the ct with the chain rule. It's going to bring down a c, and then that's going to multiply my whole equation by c. So that would work. So example. But what happens if I try this with m? Well, I would need to be able to stick a matrix up here in the exponential. And that's the thing that I want to introduce. That's the thing that we would love to learn how to do. Okay, so this is going to be a little sidebar on the matrix exponential. What is a matrix exponential? Well, what's a regular exponential? E to the x can be defined by the power series, sum going from n of n going from 0 to infinity of x to the n over n factorial. So all I need to do is take x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial plus dot, dot, dot. The matrix exponential is just defined in exactly the same way, and it utilizes the fact that all of these operations are well defined for matrices. I'm allowed to divide by constants like factorials, and I'm allowed to raise matrices to powers as long as they're square. So if M is a square matrix, then I can do the exact same thing that I did here. M to the nth power over n factorial. Great. Another thing that I should point out here in my sidebar is that just as e to the ct has derivative c e to the ct, so too does d dt e to the m times t, where m is a matrix, have derivative m e to the m t. You might worry that m e to the mt, I might need to worry about the order here, that m e to the mt is not equal to e to the mtm, but in fact they are equal. So in this case, it's no problem. I urge you, it's a very short proof to show this identity for yourself. You just need to take term by term derivatives in that series above. Okay. Now, we can go ahead and solve our equation. So we had c double prime is equal to mc prime. So the way that I would solve that is assume a solution c prime, so try c prime is equal to e to the mt times c prime naught. Right. One important part of this is that m to the 0th power is defined to be the identity matrix, which means that e to the 0 matrix is the identity matrix. So at time t equals 0, what I should get here is 1. So this must be c prime 0. Okay. So we'll try this. Does it work? If I take c double prime, this is equal to m e to the mt c not 0. Oops. Try not to bash my mic here. All right, and this is exactly the same as what I get if I simply multiply c prime 0 by m. So it works. Yay. Okay, so we have a solution. C prime is equal to, now I'll write it back in, minus 2 pi, 0 minus 1, 1, 0, times C naught prime. Okay. Oh, sorry, is equal to e to this. E to the minus 2 pi t, 0 minus 1, 1, 0, times C naught prime. Great. Okay, now we're almost ready. We can solve for C prime, or sorry, for C, but we would need one more thing. What happens if I integrate this? So what happens if I take the integral of e to the mt dt? We would love it if, as it would work for a regular constant, we could just say that this is m inverse e to the mt. And in fact, as long as this inverse exists, this is true. Which is why it's so important that we reduced our attention to this two-dimensional case where this inverse did exist. Okay. So I integrate both sides. I'm going to pick up a constant, so I'll put that constant out front. I'll say that's the vector. Let's give a new name, u. And then plus m inverse. So what's that going to be? 1 over minus 2 pi times 0 minus 1, 1, 0 inverse times e to the minus 2 pi t, 0 minus 1, 1, 0 times C naught prime. Okay. Now you might say, even though, look, I found this solution, it didn't take that many lines. So let me just point out, this is the solution. But I haven't done any of the hard work. The hard work would be in figuring out what this matrix actually is, which apparently is going to require me to multiply together ever larger products of matrices and then sum them together infinitely many times. And then I also have to find this inverse matrix. So let's take these tasks one at a time. First of all, this inverse matrix is not too hard to find just by guessing and checking. It turns out that the inverse of this matrix is just minus itself. So 0, 1, minus 1, 0 is the inverse. Is equal to 0 minus 1, 1, 0 inverse. All right. Now the second thing, how do we figure out this e to the minus 2 pi t, 0 minus 1, 1, 0 business? Here we're going to need to use that this matrix 0 minus 1, 1, 0 is very special. How is it special? Well, I'm going to seemingly arbitrarily look at the matrix I times this thing. Maybe minus I times this thing. Minus 1, 1, 0. Okay. That's not very interesting. But let's look at this thing squared. Okay, well, minus I squared is minus 1. And then 0 minus 1, 1, 0 times itself. All right, so what am I looking at here? Minus 1 can just be pulled out again. Then the top here is going to be a minus 1. Then this top right is going to be a 0. Bottom right is going to be a 0. sorry, bottom left. Bottom right is going to be another -1. So this is the identity matrix, the 2 by 2 identity matrix. That means that -I times 0 minus 1, 1, 0 cubed is just equal to -I 0 minus 1, 1, 0 to the first power. And every even power is going to be, we're going to multiply by, sorry, for every even power, we'll get the identity. And for every odd power, we'll get this once again because of this cool little property. So now I'm going to take this object that we were looking at, and I'm going to rewrite it. I'm going to say this is e to the minus 2 pi t times I times the quantity minus I times that matrix. Great. So now I can do the following. I can write this out in series form. So I have my 1 over n factorial. Now, all of these constants, so the minus 2 pi I t, I can pull out here. To the n, good. Then I'm going to have this matrix, minus I, 0, minus 1, 1, 0 to the n. But we just showed that for n even, this is always the identity matrix, and for n odd, this is always a specific matrix, this matrix. So this power series is actually equal to all of the even parts, so n even, going from 0 to infinity, of minus 2 pi I t to the n over n factorial times the 2 by 2 identity matrix, which is on the outside of the series. Maybe make sure that that's clear. And then minus I times 0 minus 1, 1, 0 times the sum of all of the odd terms in the series of minus 2 pi I t to the n over n factorial. But we know what these series are. This is, in fact, exactly the series for cosine, the cosine of minus 2 pi t. And this is precisely the series for sine. I should say for I times sine, sorry. So this is I times sine of minus 2 pi t. So now when all is said and done, this object here that we started with is equal to the 2 by 2 identity times, well, cosine is even, so I'm allowed to ignore that minus sign. And then look, this I and this I are going to cancel to a plus, but then we'll get a minus from that minus sign, since sign is odd, minus 0 minus 1, 1, 0 times sine 2 pi t. And now we're out of the exponential. We don't have a matrix exponential anymore. We just have some functions times constant matrices. All right, so now we are finally, at long last, ready to write down our solution. So we had this, and we're now going to be able to rewrite that. So xi is equal to some constant u. I have a minus 1 over 2 pi from before. Then I'll be able to change that to a plus because recall that this had this, the inverse of this matrix is its negative. So I get 0 minus 1, 1, 0, and I have to flip that sign. Oops. Times the identity matrix times cosine of 2 pi t minus this same matrix, 0 minus 1, 1, 0, sine of 2 pi t. Great. Times c naught prime. Okay, and the last thing to do is just multiply this matrix through. So we're going to get u plus 1 over 2 pi times 0 minus 1, 1, 0 times cosine of 2 pi t. Okay, and then I'm just going to remember that this matrix times itself gives me the negative identity matrix. So then this becomes plus the 2 by 2 identity sine 2 pi t, and all of that times c naught prime. Okay, so did that actually help us? Was that a useful exercise? Well, sort of, in the sense that it tells us the exact same information as the complex case did. This turns out to be exactly be telling us that the object is performing uniform circular motion in the 2D plane, in the xy plane, I should say. So this form turns out to be telling us that the object is performing uniform circular motion. It's maybe not as clear in this setting as it was in the complex plane, where I think students are probably more familiar with the way that a function tracing out uniform circular motion looks as a complex function, namely e to the something times e to the I something times t. Whereas in this case, we're getting these cosines and sines, but multiplied by these kinds of matrices, which somehow also tell us about uniform circular motion. In fact, the reason to try this third method was to start getting used to some of these matrix methods that you may see elsewhere. In any case, this lecture has principally been about introducing new techniques and practicing some of our differential equations solving strategies. So I hope that it's been helpful in that case, and I also hope that you get a bunch more practice from whatever text you're using. Until I see you in the next one, thanks for watching.